Hello, everyone, and thank you for joining us on today's Senza Fili Sparring Partners webinar on getting RIS off the ground with AI and machine learning. Our speakers today are Melike Erol-Kantarci, full professor at University of Ottawa and chief cloud RAN AI scientist at Ericsson, and Monica Paolini, principal at Senza Fili. I'm Kendra Chamberlain, and I will be moderating our webinar today. In Sparring Partners, we watch our speakers debate a topic live on video, and we would like to encourage our audience to participate. Please share your comments and questions using the chat function of the Zoom taskbar. All comments are visible to all participants, so please keep the conversation polite and respectful. Our speakers will do their best to address questions as they go along and as they become relevant to the topics being discussed. So please do not hold your questions until the end. And with that, I'll hand it over to Monica.
Thank you so much, Kendra. As always, it's a pleasure to be here. But this is a Sparring Partners that I've been trying to do for a very long time. I learned about RIS, which is Reconfigurable Intelligent Surfaces. That's what it refers to. For a couple of years. It was at Mobile World Congress. I was at the ZTE booth, and I was just going around to find out what it is that they were working on. And I found out about RIS, and I thought it was like really interesting, but I couldn't get it within the few minutes there, because it's a I think very fascinating topic, but it's a little bit complex to get your hands around it because there is so much new stuff there. And so then after that, I tried to talk to everybody that was working on it. The city has been working on it, and others as well, including Ericsson, and Mel is working on that. But it's still early days. So I had trouble finding somebody who really wanted to talk about it until I found Mel, and I was so glad that we finally find somebody that is willing to talk about something that I would say is not yet, commercial, but it has a huge promise, and it's important because it makes us think of a new way to transmit a signal that is more power efficient. So I do not want to get too much into the weeds right away. I just wanted to give you a little bit of background of why we're doing this, and so also today is going to be a little bit more of an introductory Sparring Partner. So we're going to go through we're going to provide a little bit of introduction. We don't assume that everybody knows what RIS is and what it does, which is different from regular practice. But before we all go into that, as usual, I would like to ask Mel to tell us what she's doing. She's working both at university and at Ericsson. She has 2 jobs, basically. So Mel, tell us what you're doing.
Well, first of all, thank you very much for inviting me, Monica. I think it's a great place to discuss these upcoming exciting topics in wireless communications. So my name is Melike Erol-Kantarci, and by now you know that I wear 2 hats. I wear a hat in academia. I'm a professor and Canada Research Chair at University of Ottawa. So in my day-to-day job at the university, I lead a research group of 15, sometimes 20 PhD master's students, and we do research on the cutting edge topics. And at the same time, I wear a hat in the industry. I'm Chief AI ML Data Scientist at Cloud RAN product of Ericsson. And that's also another exciting job for me, where I get to see the R&D from the industry side and do a lot of exciting projects over there as well. And RIS topic in particular is very dear to my heart, especially when it comes to the works that we did in academia. We published several survey papers and couple of RIS enhancement papers in this area, and they have been quite actually future looking, in the sense that we have worked on machine learning, because that's what my expertise lies. I combine machine learning, AI with wireless communications.
Yeah, and that's going to be an interesting part of our talk today. So RIS is number one, right? That's the main thing. But in order to get RIS working, AI and ML are going to be fundamental. So it's the combination of the two. So we'll get to both. And for all of you in the audience, do ask questions, even if it's a question now, tell us more about this, because we're trying to try to cover things, but if something is not clear. Okay, so why don't we start from scratch? First of all, to the whole, I always think of RIS, but it's reconfigurable intelligent surfaces. Can you tell us just what that is, just to get started, and then go deep?
Absolutely. So I'll start with the surface, the word surface, right?
Yes.
Yeah, I think it's very important to define it. It's a new technology, and maybe a few experts might be in the call who are familiar, but I think it's important to explain it for everyone's information. So first of all, RIS is a metamaterial. A metamaterial is a material that doesn't exist in the nature. It's an engineered material. And because RIS is thin, or it is planned to be manufactured thin so that it can be painted on surfaces, it can be sticked on top of windows or walls, that's when we call it surface. And what makes RIS interesting is that the size and the distance between the elements of the RIS, so RIS consists of actually many passive antenna elements. The size of these needs to be smaller than the wavelength of the impinging signal, so that Maxwell equations could hold and they could reflect the signal. So the whole idea of RIS is you can make it you can think about it like a passive antenna system. It's actually nearly passive. We don't call it super passive because it has a bit of signal processing capability. It doesn't have the baseband, of course. And also it is attached to a controller, and that's actually makes the intelligent part. So reconfigurability and intelligence comes from the fact that this passive antenna array is connected to a controller, and the controller is connected to AI. So that's how everything gets together.
But I think that you just explained in a very good way why this concept is so powerful and yet not trivial, because there is so many new things coming together to get a new, hopefully potentially a new way to think about the way we transmit signals. So it's not just, well, it's just a tweak of what we have so that you get a little bit better. This is fundamentally a different way to think about transmission. And as I say, it might not be entirely passive, but it's basically passive, which makes it more energy efficient, and also lowers the cost in a way that you can do different type of deployments. You can use reflection, and it's not like reflection is nothing new. We knew about it, but we have not been able to use it in such an extensive way. So this is one way to go. Okay.
Maybe we can add to that, Monica. I think you mentioned something very good, that it's not a tweak to the existing transmission and receiver systems. It's actually new because we are manipulating the radio environment. Because up until now, the optimization in wireless networks has always been like, how can we transmit better, or how can we receive better? But we weren't thinking about that the wireless propagation environment was something that we can play around. But with RIS, actually, we're modifying this. We're modifying the radio environment and making it a smart environment.
Absolutely. And I guess that, sort of at a very high level, it really kind of works well with our increasing. So, okay, so let me start back. At the very beginning, you have, like the 2G networks, which is like, we want to cover everything, but only a few devices out there. scattered. And now we get to a sense of pervasive connectivity. So everything is connected. Everybody has at least a phone and more devices than their IoT. So you just need to connect everything everywhere. And so I think that RIS is a complementary view from an infrastructure point of view, where you do need to have the infrastructure supporting the connectivity in a more spread out and more sort of everywhere. Because with RIS, you're going to have many more points where you transmit. So it's no longer the macro kind of idea, or even the small cell. It's like all over. And so connectivity become more of a pervasive thing,
Right.
both for
Almost like,
infrastructure and the device side.
right. Almost like transmission and reception becoming ubiquitous, right? You have
Yes.
actually, you could cover as many surfaces as you want with RIS, and then you would have the capability of manipulating the signal as if you're putting transmitters, but of course not amplifying the signal, but changing different properties of the signal. And I think that's one thing we need to talk about too, right?
Yes.
Because what are we actually changing in RIS? Is it the amplitude of the signal? Is it the phase? So it's actually not the amplitude. We don't want to play with the amplitude, but we want to play with the phase of the signal. So we want to do a phase shift of the signal so that the signal coverage can be optimized. But yeah, I mean, as you said, it's a new way of treating the environments and taking things to kind of anywhere, or ubiquitous concept.
Absolutely. Okay, so let's get to how does that work? You know, that seems like, you know, so when I heard the first time, it's like, passive? How can you do that? You know, it's again, it's an entirely new concept. So can you tell us why is it working? Why don't, you know, how do we come up with that? And why is it, was it good anyway?
Right. And when you hear such a simple idea, you always start to think, why we haven't thought of this earlier? Like,
Yeah,
why now?
what is an old passive? I mean, okay. Yeah, there is an obvious question to that, but you know, yeah, why now? Why is it? Yeah,
Yeah,
and how does
exactly.
it work? Is that magic? You know?
Well, actually, no, it's not magic, but actually, I mean, the reason of timing is, of course, because the availability of such small passive antennas and also their size in relation to the wavelength that we use in communication. But as you know, if we just try to explain like how these work, you can basically think like the surface is having two layers, and as the layers shift, we can change the impedance of the circuits, the pin diodes, and this change in the impedance allows us to convert or change the phase of the signals. So it's a signal manipulation, but manipulation happening in the phase of the signal. We can't change the amplitude. It's a passive element, as I said. We can't change the frequency because we are bound by certain frequencies. It's only the phase that we can play with in the wireless domain. And surprisingly, it's actually a very powerful thing if you can play with the phase of a signal.
Mm-hmm. Right. And so what that allows you to do is, you know, you basically you're using reflection to, I mean, we use reflection already. And in fact, Ericsson published a paper quite some time ago about how reflections is very helpful, even if you have a, you know, sort of a in line of sight. I mean, if you go like millimeter wave, sort of high frequencies, well, I guess everywhere, but you know, you can actually use reflection to your advantage, and everybody knows that, but you cannot do it in a obvious, I mean, in a reliable way. But with RIS, it becomes more center, and in dense environments, like in a city where there is clutter everywhere. So line of sight is a limited luxury. So how does the reflection part come in?
It's actually, I always like to call it that way. Multipath is a bliss and it's a curse for the wireless communications.
Right.
And reflections are part of it, right? We have structures all around when we talk about outdoor communications. When it's indoors, we have the walls, windows, and all the furnitures to create actually surfaces that a signal can hit and can be reflected. So if the reflection can be controlled in such a way that the signal is condensed and the power is directed to a certain direction, then we can make gains out of it. But if it's not controlled, then it makes the multipath effect of a signal, which makes it difficult to handle at the higher levels because it gets into a symbol, it gets into the way of the other symbols that are coming right behind them. So it's a tricky area to optimize, I would say, but definitely, I mean, RIS is basically being the master of reflections in the wireless domain.
And I guess that's kind of part of the sort of magic part of it, is that you can start, and I guess increasingly in wireless, we're learning to use things that traditionally were a limitation to our advantage. So for instance, the fact that you cannot have indoor coverage because of the walls, that allows you to do more indoor infrastructure without interference with outdoor. So everything kind of is a mixed blessing here. And so, you know, you can do it. Okay, now let's look at that. Okay, so we understand you can have those panels, you can use reflection, and you can use RIS in any frequency you want. But most of the attention right now is on millimeter wave, correct?
That's right.
Why is it so?
Well, one of the fundamental use cases where we see RIS will be very, very helpful is coverage. So when we have blockage, where let's say we have dead zones in a building where we have corridors that the wireless signals are not penetrating, we need to find a solution for that. And RIS over there comes as a good alternative, or not an alternative, but a good supporting, augmenting structure to deal with these dead zones. Similar dead zones can occur in downtown areas where you have the high-rise buildings and areas as we call as canyons, urban canyons, where the signals have hardship in reaching from the top of a high-rise building to the users, let's say pedestrians who are walking on the pavement. So having such a reflective surface actually helps increasing the coverage. And I think that's why we are saying or seeing RIS as a technology that's agnostic to the frequencies, but because essentially you could reflect any frequency, but when you have frequencies, like when you work in the frequency ranges like millimeter wave or terahertz, where blockage is a big problem, then RIS can be a good helper for you.
Yeah, so, you know, so you can use it like, you know, the typical cellular frequencies, but it's just like there is no immediate use case. I'm sure that there might be eventually, but that's not what. So it's the way I think about RIS is it's a way to densify the infrastructure at a much lower cost and better granularity. So it's more effective in densifying, but clearly because it's passive, it doesn't have the same. So if you compare a RIS panel with a small cell, clearly the small cell has more power and therefore has better reach. However, because of that, you know, you have more of an issue with potentially with interference and things like that. It's more expensive, it needs power. So the advantage of RIS in really this kind of really dense environments is to provide the kind of fabric of connectivity that requires a dense infrastructure, which you can have with RIS because it's cheaper. And maybe we can get to the cost in a second, or maybe you can comment on that.
Right. I mean, yeah, I think as an augmenting structure, it's really, really powerful. It's not probably going to replace the small cell base stations, but we have shown, like in our research papers, that it's possible to put some of the small cell base stations to sleep if you have RIS infrastructures, because you would still need the baseband processing to handle the users in a certain domain. But let's say you have fewer users and you just want to have them attached to the macrocell base station, then how do you deal with the users that are in non-line of sight? Then you can actually turn off your RIS and quickly at a low cost have the coverage for those users, have your small cell base station sleep, save energy, and that would be like coming at a low cost and a sustainable network deployment.
Okay, let me go back to that, but I would like to remind the audience that there is no Q&A at the end, that you need to kind of get our questions in now. And especially here, we might not be covering basic things that, are not obvious to all of you guys in the audience. So don't be shy, and you can ask basic questions. Usually we get really kind of, very focused questions here, but feel free to ask general questions because this is such a new topic. Now, let me ask, and this is something that at the beginning I was kind of struggling with, with RIS. So you're going to be using some same millimeter wave band, and clearly it's passive, but it is still an issue of how does that infrastructure relate to the macro and potentially small cells that you have operating in the same band? Because one way to think about it from the overall network is that you're not going to use RIS and then not have macro or small cells. It's complementary. And it's kind of opportunistic because it's not as reliable as a macro cell. That's just, it's not the same thing. So you need both. But you also need to coordinate, because if you're using the same band or whatever you're doing, how do you coordinate macro, small cells, and RIS?
That's actually a very, very good question. And it's an open problem, I should say. We don't have all the solutions, but we have part of the solutions. And yes, one very important thing is that how do you coordinate, or even before coordinating, how do you make sure that the interference that may be caused by RIS is not impacting the users? And you have to be careful about what you do in the downlink or uplink communications, because uplink devices will reach out to the macro cell station with less power. But I think over here, machine learning comes in as a good solution technique. But I mean, I'm working on machine learning. Of course, I can talk for hours. That's my passion. So you tell me when to stop. But I have to say, like, it's not the only technique to control or configure RIS so that we could make it friendly for the existing infrastructure. We have optimization, heuristic algorithms that we can use as well. But maybe I should take
a can you, yeah, and I want to talk about AI, but can you sort of give us a sort of a high level view of how do they, because you have all the traffic. So I'm staying there with my phone. Am I connecting to macro or RIS, and how does the network or the operator decide which way I am going to go?
Well, first of all, I mean, we have to be aware that we don't have currently RIS infrastructure deployed in any of the current 5G deployments. It is a technology that we consider could be useful for 6G timeline, or it could be even further. But let's assume we have RIS and we have our UEs, and well, we have two options actually here. For RIS control, UE actually can be the controller of RIS as well. So as a user, you might be saying that, oh, my signal quality is not really good here, so maybe I should turn my RIS control feature, let's say in our futuristic phones we have this, so that I can control RIS in a way that will help me communicate with the best signal quality base station around. That's one possibility. Another possibility is that the base station can configure RIS to be compliant with what's going on with the environment, or RIS can be autonomous. It could decide what to do by itself. So we have these three options. But I think behind all these things, the controller side of RIS is very important, because previously we said RIS is near passive. And then when I talk about all these control types of things, people might be thinking, wait, if you don't have power, how are you going to do the control, right?
Right.
So what we think is, I mean, not what we think, but how RIS is implemented is that it's a thin surface, but then it comes with a controller, a low power controller that can run certain algorithms. The algorithms could be simple, but they could be offloaded from different places. They could be offloaded from UEs or the base stations, or the execution of the outcomes of the algorithms could be offloaded to the controller. But in a sense, the controller should be able to change the phase shift of the RIS so that it complies with the signal environment.
Okay, so I want to go to the AI and ML part for sure, but that was going to require a little bit more time because I want to make sure we get it covered well. Let me go back, and I guess that one way to think about it is that the antenna part is passive, but then whatever management you need to have, that is going to require energy, but power, but that is a small part. So if you think about a base station, small cell, macro cell, whatever, most of the power consumption is to transmit the signal. So the management part, you might require some energy, some power, but not as much as you would in a say in a small cell. So yes, you do need some power, but it's not going to be comparable to even a small cell. Is that right?
Yeah, I mean, transmit power
Yeah.
takes a big portion of the energy, and with RIS, obviously, we don't have that yet.
Yeah, so to say that it's completely passive, it doesn't require power, it's a little bit, it's not necessarily entirely true, but it is true that the transmission doesn't require power. Just what now we have a few questions, so why don't we go through them and then go back to the issue of optimization, because I think that this is really, it's a really cool part of it. So I want to make sure we have the time. So what the first one is the price point for a RIS module. And then where do you see them deployed, first indoor or outdoor? Okay, I would say let's keep the indoor outdoor part of the question for later. It's in our topic, but can you talk a little bit about the cost of the
Yeah, these are expected to be low-cost modules. Of course, today we don't have them commercially available. We have them in labs. Several universities in the US, Canada, Europe, and Asia have these RIS prototypes, and also vendors are looking into prototypes as well. When there is mass deployment, I would say the expected price of RIS would be very, very low in comparison to any kind of antenna equipment. But again, you have to think about the cost of the whole infrastructure when you look into a RIS module. RIS cannot operate on its own. It can be an augmenting infrastructure, but still in comparison to any active antenna, it's expected to be low.
Yes, so and that was going to allow us to think of the RIS panels to be really spread out, because then you can use again, yeah, you can use reflection, but it's just so reflection you can use. So you want to have, I guess a crucial part is to have a more dense infrastructure.
Right. And I think when it comes to cost and MNO perspective, it's also very important to think about like how you deploy them, because that's a part of the cost is too, right? It's not only the antenna cost, it's where you deploy it, the real estate cost, and the also the aesthetics in the city. So RIS actually can be quite aesthetic. It could be a material that's just hidden in an advertisement pane, or it could be painted on some windows. So in terms of that also, it reduces the costs and aesthetic view of the deployments too. It improves the aesthetic deployments.
Okay, so we have 3 questions from Mahmoud. So the last one is why there is no dependent controlling algorithms for reasons for night times. And I think that's what you can have, right? I mean, that's you just have whatever controlling algorithm you want. And then there is another question about, is this autonomous control can be realized with other UE's information? Because you're collecting some data. And then the third one is about RIS materials. Is it possible to play with the chemical structure of the surface to enhance the quality of the signals? Do you want to address those questions, and then we can move on AI?
Sure, absolutely. First of all, I mean, it's an active research area. It's about the PNT composite transformers that the transistor community is trying to improve to get RIS better. So I'm sure there are ways to improve, and it's a topic that people have been working on. When it comes to the other questions about autonomous control, like whether we could do the control by using other UE's information, actually, I think it's better to take this question when we talk about federated learning, because federated
Yes.
learning is a machine learning technique where you don't actually have to share information. So each UE can have their own federated learning agents, and then they only share the weights of their neural network rather than the inputs of the neural network, and they can optimize systems. So we see that there's a potential to optimize risk by using such a technique as well. And then when I get to the last question, I go in the reverse order that
Sure.
you asked, Monica, but I think Mahmoud has input the questions in that order. So time, well, dependence of the control algorithms to time, and also whether it can be used to say power of the base stations. I mean, absolutely. As long as you have the proper control mechanisms and also wake up mechanisms, right? I think this is one of the most important things when you think about sleeping cells. You want to be able to activate them on time so that they can handle the necessary traffic. So as long as you have these proper control algorithms, it is certainly possible to use in such a way.
Okay, so we're going to get to the question about indoor and outdoor and reach in a second. But let's talk about the AI and ML part. And, this is another area where oftentimes there is a sort of misunderstanding out there. So like people think that if you add AI and ML out of magic, everything will work better, or you will have a ChatGPT thing. And it's like, no, it's a little bit more than that. There is more different tools. So why don't you tell us why, how specifically AI and ML are going to help us here? So that it's not just sprinkling, it's not just putting salt on that wrist and then it works better. It's more than that. And why do we need it with this specifically?
And I mean, in general, why do we need AI in wireless networks? I think it comes with the consideration of complexity. The complexity of wireless networks has been increasing from the 2nd generation till the 5th generation, and then finally in 6th generation we're dealing with very, very complex systems. That's number one thing. And number two is that we have more data than before. So I mean, a lot of the people think that, I mean, we have some data from previously, and we're all, of course, I mean, developing wireless communications and algorithms around some data. It's not like, we have some hypothetical algorithms running in the networks. They are based on data as well. But as the amount of data is becoming more and more, it's becoming increasingly challenging for humans to comprehend the data, because we deal with multidimensional data coming in a correlated sense. So that's where actually we can use machine learning and AI algorithms to help us to make sense of the data. And now we have the best of the both worlds, right? We have the data, we have computational capacity, and we have those control problems. So we have the, all the ingredients that you need to have in your hands before you start solving a problem with AI and machine learning. And maybe we should take a step back and talk about the general machine learning algorithms and say how they can be applicable to this area. And, I wear my professor hat and I go very categorically when it comes to machine learning techniques. So a very fundamental machine learning technique is supervised machine learning. So in supervised machine learning algorithms, we have labels of the data. In any kind of wireless network, it's very hard to have labeled data because there's a huge amount of data coming from the base stations. But when it comes to RIS, for instance, what can be done is we can use CSI prediction by using partial CSI information. Like if there's some useful automatic labeling scheme that you have in hand that you're using CSI, then you could actually do it to predict the other CSI values, and that's something needed for RIS. When it comes to unsupervised learning, we talk about unlabeled data. So we talk about clustering the users. It's basically driving some information about the data that you have in hand. It's unstructured data. You can't really make sense of it. Then you map it into different dimensions, and you see in certain dimensions that the data shows some clustering behavior. So this could be actually in the RIS context, could be that you map channel conditions. and then you say certain channel conditions are giving this risk configurations to you, or you're doing better with such and such risk configurations, then you can say, this is the proper type of clustering and using the same configuration. And then a more interesting machine learning algorithm type is actually reinforcement learning. And my group does a lot of research in this area. Actually, for the interested audience, I can input some of the references of our papers that they can look into that, both in terms of RIS and how we apply machine learning, and in general, how we use reinforcement learning for wireless communications. Well, reinforcement learning is a technique. Actually, it's a very exciting technique, in my opinion. I mean, it's different than the other machine learning techniques because it's where it tries to mimic the human learning by trial and error. So that actually touches on to a lot of control algorithms in the wireless world and robotics as well. I mean, wireless is not a singularity. RL is used a lot in this domain as well. And if we are talking about control specifically, then RL becomes very important. So we can configure the phase shift of the RIS elements by using reinforcement learning. And it's also on-off of the elements. Like, we don't have to keep the whole RIS surface on all the time. We can actually configure turning on and off certain portions, like certain squares on the big surface, if you want to think about it, and turn them on and off to help us with the reflections that we want to control, to direct the reflections in a certain way. Then federated learning, I think when I was answering the question about how we would train at the UEs, that came up. It's certainly possible that the training is done on the UEs, and then they come with a control approach that suits for each individual UE, and they apply their own policies. We can use graph neural networks, which is a newer type of machine learning technique that would learn the intrinsic properties of the wireless environment and would configure RIS again. And then hierarchical reinforcement learning, which actually my group made quite advances in this area as being the pioneers in the area, where we said if we have different time scales, like if we're looking into cell sleeping, which could be in the order of minutes and hours, and then looking into phase shift control, which could be in the order of seconds to milliseconds, then how do you manage this control at the same time? We came up with a semi-Markov decision process and hierarchical reinforcement learning scheme to address this problem. So I can go deep and deep in this topic, but I don't want to bore everyone with machine learning.
This is really fascinating. We should have a separate one just on how you can use AI machine learning in wireless, because there are some concepts that are kind of it's just not RIS, it's just everything, and it's really fascinating because I used to study AI and ML, and it's interesting that a lot of those concepts and techniques are quite old. I mean, the conceptual part, the theory. It's just that we couldn't do much of it, because I said we didn't have the computational power. You'd have to hire to get room on the supercomputer, whatever, and we didn't have a problem. I mean, we did have, but not as compelling as now. So now we have. It's like it's the right time. But still, it's not trivial, and you have different choices in what is appropriate. Now, with respect to RIS, there, as you mentioned, there are different sort of different levels, different timelines, and different ways in which you can optimize, and you kind of have to do it all in order to really get the RIS to work. So, on day one, you deploy the network, so you want to know how to deploy it. Okay, where do you put the panels? And maybe that AI can help you in the planning phase. But then once you have it, you need to do the basic settings. And that's one thing. And when you have that kind of learning, is it centralized for the network, or is it specific to a location? So basically, you do some learning that just works for the whole network, but then you might have each base station learns its own environment, and then every RIS panel. So how is that spread out locally? And then you get more and more into the real time, where you just, okay, I have this basic configuration, which is good baseline, but then the sleeping pattern, that's going to be dependent. I mean, some of it might not be dependent on time. You can use historical data, but some is going to be dependent on time. And then you can get into the real time milliseconds. And then when you start talking about, like, beamforming and things like that. So can you tell us how you optimize things as you go from one to the other? And then the other dimension is that, is it going to be from the base station, from the RIS panel, or for the UE? And maybe it's a combination of all of them, but how do they get together so they don't kind of fight with each other?
Very good questions. And actually, I can say, if someone asks me what keeps you up at nights, I would say this whole thing, right? Because it's a very complex area, of course. Whether you do whether you use machine learning in a centralized manner, you distribute it, how much you distribute it, and the amount of possibilities or the combinations actually makes it very challenging, but at the same time very promising as well, that you can pick and choose the best alternatives in between. I don't think we are at the point in terms of RIS where we can confidently say, okay, centralized algorithms are the best for RIS. We do this time scale and this and that. There's still research ongoing in that area. But I mean, it's almost obvious that you can centralize everything with machine learning, especially if you think of a big domain that you want to optimize, geographically big domain that you want to optimize. Of course, different behaviors would be shown, so you would need to localize some of these learnings. But then, how much you centralize, how much you localize, these are all optimization metrics that you want to think about, like how much training time you want to allow for, and then after training, how much inference time you can allocate, and then what's the accuracy that you can accommodate the machine learning model. Because even the rule-based algorithms come with some non-accurate predictions or results. So you have to sort of make a calculated decision on what you want to do with machine learning and how much accuracy you want to reach with the algorithm that you designed, and the cost has to be comparable to that one. There is this trade-off of making things really, really perfect on one side, and then having the huge computational cost of AI algorithms, and then maybe compromising a bit of your optimality, and then coming up with a simpler solution that has less cost. I think all of these things are really very good questions and active research areas.
Absolutely. And I guess that there is and as you say, well, this is a work in progress, but I guess there are different ways in which AI can contribute. And if you think about it, of having RIS without AI and ML, that would be very hard, because there's so much coordination that has to go on, and so much optimization, because clearly you're starting from it's not a brute force approach. Like if you okay, macro is kind of brute force. You just put the macro, blast whatever you can, and this is a little bit more. It requires more fine tuning. So you cannot. So okay, I just see that you put you post your article.
Yes, and something very interesting. The second one is on heuristic algorithms. So I talk a lot about AI ML, but I don't forget the other type of algorithms. Like optimization is a strong tool, of course, but then its feasibility in the real domain and practice is very limited. So as I was mentioning, the trade-off between the cost of an algorithm and optimality, then heuristic algorithms comes at a less optimality point, but then they're low cost. So we did some research in this, and I wanted to share with the audience.
Yes, no, absolutely. And that is and I think that's something to keep in mind, at which point you might not want to go too far out with the AI and ML, so you need to keep it all in perspective. I see that some people are raising their hands. We are not taking we are considering it, but we're not letting people speak. So if you have questions, just write it in the Q&A or in the chat. Okay, why don't we go to some of the question? I think that the first one is about indoor and outdoor. So the question is like, how do you see the indoor outdoor? And there is also a question from an operator in Canada. a neighbor of yours, they tried millimeter wave, and they saw that it didn't penetrate in indoors. And so how can RIS help in this scenario? And I saw the very first, as I said, the first time I saw the ZTE demo, they were having something that you put on a window, and then it would kind of, so it goes from outdoor, indoor, from outdoor to the window, and the window just reflect indoor. Well, it's not, sorry, it's not a reflection, it's just, you just send it indoors. And so there is that you can go inside from the outside to inside, or you can just use it in the indoor environment. And I know that that's kind of now a very popular view, but I think that the kind of RIS type of solution for indoors, I think it's potentially very useful. But that's kind of like, I don't see a whole lot of support for that. So you can talk about, is indoor, outdoor, both?
Well, I think research-wise in the academia, we see a lot of research in outdoors. But when we look at the prototypes, we see all of the prototypes in indoors, almost all of the prototypes in indoors. From my own experience, I've seen several prototypes in Northeastern University from my colleagues where I collaborate with. And they have done a mobile demo with that as well, like having the antennas on a car and then using RIS. And when it comes to the operator question from Canada about using RIS on a glass and allowing the signal in a certain way of, reflecting the signal or directing the signal to indoors. Yeah, we have certainly demos from academia who have successfully shown that this is possible. But unfortunately, we don't have the commercial deployments or commercial tools yet to bring them in. And one of the major reasons is that the effectiveness of signal amplification is still too low. I mean, on a theoretical sense, you can show that by tuning RIS, you could allow some penetration indoors, but it is still very limited coverage. You would still need some supporting infrastructure indoor to amplify that signal and reach the UE in a meaningful way that you could provide some capacity. So when we say usually indoor usage of RIS, we assume that the transmitter is also indoors and RIS behaves like a reflecting surface. But from outdoor to indoor signal carrying, that's still a bit of, I would say, a research area that we need to improve the operation of RIS before we can think of commercial use.
Well, one different way to look at it is that if you cannot go from outdoor to indoors, you don't have interference, so you can have the indoor infrastructure completely independent from the outdoor infrastructure, and you can in terms of spectrum reuse, it's a good thing, because you just can have, you could imagine that within your apartment or within the enterprise, your office space and whatever, you can have your own RIS, and it doesn't interfere with whatever is happening outside.
Actually, it's very interesting that you mentioned that, because RIS, I mean, maybe, yeah, it doesn't come to mind at first, but RIS has a nulling property as well. So you can use RIS in security use cases, that you can null some interference and do some sort of geofencing. And just like you said, I mean, it's possible maybe to make chambers of better communication when we try to operate in different bands.
Yeah, actually, yeah, the ETSI report, which is I recommend. So I don't have the link here, but if you go to the ETSI page, they have a couple of papers on RIS, and they talk about all those sort of geofencing security use cases, which, yeah, you don't necessarily think about it at the beginning, but in some cases it might be relevant. It's not going to be relevant in our homes, but I would imagine. But there is that aspect as well. Okay, so indoor, outdoor, both. There is another question about tracking individual users in real time to aim the signal. And I think that what that might refer to is the fact that you can be using beamforming. I think that the ETSI calls it the transmissive RIS. I know that ZT is working on so that you can use beamforming. Again, what that does, it increases the power requirements, but on the other hand, if you do some beamforming, then you're going to improve the performance. So Mel, how do you see, do you need that kind of how important it is to do like a beamforming type of use beamforming for
Right. I mean,
that?
definitely RIS can condense the signal in a certain spot and amplify the effect of the receiver in terms of transmitting signals in altered phases. But user tracking would require some sort of baseband processing. So at the moment, unless we start talking about active RISs, which would become expensive equipment, almost some sort of replica of a base station, then we can't really track users with RIS. But what we can do is, once a UE is associated to a base station, we can improve the signal path for that UE by beamforming in such a way that the especially the millimeter wave signals or higher frequency signals can be better propagated.
Excellent. Now, follow-up question on this is to coordinate to improve performance, to use RIS to coordinate, and sort of related to that is that can you use RIS to reduce the signal so that you can reduce interference? So I guess the question is how to coordinate it. And in fact, I mean, because clearly you want to reduce interference, and you mentioned before you can use the sleep, you can put to sleep the small cells or rest, depending on what you're trying to do. So how does that work?
Well, I mean, coordination is actually in the essence of machine learning, right? With machine learning, we would like to coordinate RIS, but I mean, there are different levels of coordination. The first coordination, of course, needs to happen with the network infrastructure, because RIS has to be a friendly augmenter of the smart radio environment. So it has to support whatever communication is going on. Then the second level of coordination could be among RIS. And actually, this has been considered also in the report that you mentioned, Monica, the ETSI report, that you could actually put multiple RISs almost like facing each other, where they would make the signal basically reflect from one RIS surface to the other RIS surface and then reach the UE. So it's actually, if we can coordinate two or more RIS infrastructures together, that brings up far more opportunities to optimize.
Absolutely. No, yeah. And I guess that's really what the work is about, to how do you get it to work. I mean, how do you optimize it to a point that it's really you maximize the usefulness. Now we have a question on the models. How often do you need to train the models? And I think that's would be an ongoing, I mean, you get started, but it's a never-ending task, isn't it?
Right. I mean, in machine learning, any kind of machine learning tasks, if your environment is changing, you have to consider about retraining. Sometimes one model could be sufficient for multiple different situations in the same environment, so that you don't have to train so often. But some environments would be so dynamic that you would have to actually train your model again and see if you can find a better model. So this actually is quite an environment dependent question, actually. When we look at it in our research, we try to do it in a very stabilized environments where we have the channel conditions, saturated to certain levels, certain number of UEs, and the mobility models are input in a certain way that we don't trigger the training so often. So we would have a time to use our discovered model. But then when it comes to real world, of course, that's a question that you need to have in mind. You need to have a mechanism to control. Well, first figure out whether you need retraining depending on the dynamicity of your environment, and then if you need it, that you have the mechanism to be able to do that.
Absolutely, yeah, and that's, I mean, I guess that's the same thing as life. You just want to keep learning. You don't want to, whatever you do, you just keep going. Now, we have one more question about interference, but I think we kind of addressed that. But maybe we can talk a little bit about just to make sure we cover it, the standardization process, because well, I guess, in a way you don't even need it, but it's helpful to have it. And ETSI is leading here with the standardization. Is 3GPP doing much on it as well? And how do you see that path?
Mhm. Yeah, I mean, I share your view there. I see ETSI being more active at the moment and 3GPP not being so active, but it is a very active area in academia, also in industry research branches of many vendors, just like Ericsson. I'm sure they're looking at the RIS technology. Sometimes we go public about this, sometimes we don't, but usually these kind of research areas which are promising are of interest to multiple parties, and then when they come to a certain maturity, they get to be discussed in standardization bodies as well. And I see it as a very positive thing that ETSI has a work group around it, and we may expect something like that in 3GPP soon.
Absolutely, and I guess that as soon as the vendors are more openly active, I would say, because yeah, it's easy to talk to people, but again, it's still a little bit, it's a bit early days, so that a lot of the vendors are not really talking much about it, which I think is too bad, because you want to get people to get ready to start processing it, and looking forward. Do you see any difference? Because as I said, I got through ZT. There's in China, there's a lot of activity. It's actually more in the sense of press releases and things like that, trials. But also in Europe, I find more people to talk to. When I get to North America, less so. Is that the way you see it?
Europe is very active. That's what I'm seeing as well. And I think the way European projects, especially in academia, are structured then has been fueling this area a lot. I have actually a lot of colleagues that I collaborate with who are in large European Horizon projects and who work in this area. And of course, these projects have industry partners as well. So industry is involved. They're not outside these discussions for sure. In US, you are right. I mean, I've seen a few labs. I have collaborators in Northeastern University. I've seen their prototypes. MIT has a prototype as well, and a couple of other universities as well. And then I guess Asia is also having activities in this area as well.
Okay, so and then the follow-up question is like, okay, when can we expect to see commercial deployments? And then, obviously nobody knows, but what's your view in terms of how much do we need before we even can get, like large trials, pre-commercial trials or commercial? Because you mentioned at the beginning 6G, but RIS is really independent of any, 5G, 6G, or whatever is next, to some extent. So how does that, what should we expect in terms of timeline?
Yeah, I mean, it's very hard to have a crystal ball and give you a very accurate answer on that, but maybe a couple of things. Well, first of all, RIS is a promising technology, and it's frequency spectrum agnostic, so it can help us in many generations of communications. It could even be like in the earlier generations we could get help, but when we look at the timelines, I think we would look further from a 6G timeline. It could be a technology for 6G, or it could be further, and one of the reasons is that technologically, yes, there are some challenges. Like we still need research and development and on robust and flexible practical control approaches. Commercialization is of course a big parameter here, and often in the academia we can come up with a good technical solution, but if you can't have the commercial model, that usually don't go well. Manufacturing mass production of RIS panels is something that we don't have yet, so that has to have some readiness. We need to have low complexity solutions. On the technology side, RIS still is challenged from rapid channel sounding that needs to be there, and then lacking a baseband unit is also limiting RIS to be well, I don't want to say a useful technology. It's definitely a useful technology, but with maybe a little bit more signal processing power, it could actually achieve a bit more than what we envision today. But all of these are tied to technical challenges, plus, you know, how you commercialize things. Once we get everything, I think, off the ground, we can confidently say, oh, RIS is now ready for deployment. We're not there yet, but I believe, you know, closer to 6G timeline, it would be when, you know, we can at least start giving some timelines.
Absolutely. You know, the way I think about RIS is sort of like a MIMO that, you know, it took forever to get off the ground, but it was like, you know, from the beginning, you know that conceptually there is an opportunity. The question is that, you know, how long does it take before you get it to work in practice, and then operators actually deploy it. But you know, I think that that's good. We're at the top of the hour. I think there is much more, and I think we're going to have more, you know, sparring partners or other things on RIS is going to be it's going to become more of a hot topic or well discussed or well known topic in the future. So I would like to thank you so much for, you know, for talking about something that is so interesting and yet not well known yet. So thank you so much, Mel.
Thanks for having me, Monica, and thanks for the audience for the great questions.
Well, thank you so much, and and thank you for all you in the audience and asking great questions. And Kendra, over to you.
Okay, great. And that will conclude our webinar for today. A recorded version of today's conversation will be available at sensafili.com in the coming days. Thanks again, and we look forward to seeing you at future events.